Lesson 3.5, Exponential and Log Models. What we should learn. We should recognize the 5 most common types of models involving exponential and log functions. We're using exponential growth and decay functions to solve real-life problems. And then we'll hit some other things. So the introduction is that we already did exponential and log models earlier in this chapter. So we did like stuff like APERT, and we did stuff like a logistic model like this, like that. There's actually lots of types. There's even 5 more that can known. So a generic exponential growth model is seen like this: y equals a e to the bx, where b is greater than 0. It's growth. And then we have an exponential decay model that looks like this: a e to the negative bx. These will all be given to you. A Gaussian model that looks like this, right? It's an exponential but fancier one. A logistic growth model, something like this, and then the normal log models. So here are the basic shapes. I'm not gonna have you guys memorize most. Well, you should know the E1, and then you should know how to do negative E. But I'm not gonna make you memorize all these. This one should be familiar with them and know how to use them in your calculator. So exponential growth, exponential decay, a Gaussian model. Logistic growth model is a nice one because it has like a hard cap. It's one of these that has a horizontal asymptote on top that like steers ahead, and the natural log and a log model. So these are the 3 models we're going to use with our calculator today. Example number 1 is about the world population, how it's growing. So here's it in data form, graph form, and here's it in table form, and then here's it in exponential growth form, like the formula. And it wants to figure out, according to the model, when will the population reach 7.1? So we use lots of ways. We could do it with the graph. We're going to use some algebra here. So the key thing with this is that 7.1 billion, our table is going in millions. So we want to figure out when this is going to be 7.7100. That's millions into billions, and it's a little confusing. So all we're going to do is exactly what they say. When does this thing reach this? So set it up. So 7100 equals 6097 e to the 0.0116t. All we gotta do is solve it using some algebra and a calculator. Let me bring a calculator out here. We're gonna need that for sure. So we just want to get t by itself, the variable, the exponent. So first thing we're gonna do is divide by 6097, and we're gonna get e equals e.0116t equals about 1.16451. I could use a calculator, but I have the answer right here. So we get that right. Next, we gotta get rid of the e. So remember the way we do that? So you take the natural log to both sides. Natural log, it lets you move this guy to the front. Basically, natural log you cancel out. Over here, we'll just leave it in here for now. Right, and those two cancel out. We get 0.0116t. And all we have to do now is get rid of this. We're going to divide both sides by 0.0116, 0.0116, and we get t equals approximately 13.1. And since 2013, since t equals 3 equals 2003, this must be 2013. In the year 2013, the world population will reach 7.1 billion. So that's how it's going, right? So they wants to know when does it reach that. You just plug that in for the population and solve. Example 2, in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies. After 4 days, there's 300 flies. So essentially, we have a couple points. We have 2 and 100, and we have 4 and 300. We're trying to figure out what's it at 5 and blank. Right, so we got to come up with an equation with using these 2 points. Now, they do tell us it's exponential growth. If you forgot that already, up here, an exponential growth model is y equals a e to the bx. So we have y equals a e to the bx. Well, we have two. What we want to do is we have 2 variables, right? A and b we have to figure out. Well, we have 2 points, so we can use that to figure out a and b. We're going to set up 2 equations with these 2 points. So this first equation, now remember when we set up, this is x and y. So we're going to have 100 equals a e to the 2b. Like that, because I'm plugging in for x and y. And then over here, we're going to have 300 equals a e to the 4b. And now we have 2 equations to nodes. So the next step is you want to try to solve for one of the variables, which in this case is a. We're going to try to get a by itself. Now, which one do you pick? You usually want to pick the one with the smaller power. So we're going to pick this one, get a by itself. So let's divide by e to the 2b. We're going to do some substitution. We're going to substitute that in for the a over here. And we get 300 equals 100 e to the 2b times e to the 4b. What happens is right here they reduce. Now they have the same denominator. So what's going on is it's e to the 4b divided by e to the 2b, which just means it's like having x to the 4th over x squared. You just subtract, right? You go 4 minus 2. Same thing here. We're going to, since they're the same base, that's going to be e to the 4b minus 2b, which is e to the 2b. So that's what's going on there. This is going to be 300. These are reduced to e to the 2b. We're going to get 100 e to the 2b. Now we're just going to try to get e by itself, so let's divide by 100. You get 3 equals e to the 2b. Now remember the way you get rid of e's, you take the natural log of both sides. Natural log and natural log. These cancel out, you get natural log of 3 equals 2b, and then you divide by 2. So natural log of 3 over 2 equals b, which is just a decimal. We put that in our calculator. Natural log of 3 divided by 2, 0.549. But we get b equals 0.549. So I have b, so I got to find a. So how do you find that? That's actually the easiest part, hopefully. You just go back and plug it in. So you have 100 over e to the 2 times 0.549 equals a. Just plug that into your calculator. Again, I'm getting a little messy now. I have no more space, and I get 33.3. So a is 33.3, and we have everything we need. A, we have our b, so we have our equation. Y equals 33.3 e to the 0.549 x. That's our equation, but we're not done because it says how many fruit flies are there after 5 A's, so we have to plug in 5, substitute 5 in. So we're going to get 33.3 e to the 0.459. It's a fifth. Put that all into the calculator. I'll save us some time and just get the answer in about 520 flies. So that's the answer. So that's the idea if it's an exponential growth, you do by hand. Get 2 points, plug it in, set up 2 equations, use substitution. You generally want to get the smaller one by itself, and then you plug it into the bigger one. Stuff will cancel out. Once you get one of the answers, you plug it in, plug it back in to find the other answer, and rewrite it all. So that's the idea there. How about carbon dating? It's a method to figure out how old like anything in the world is, because we all have like carbon isotopes in our body, and then there's non-reactive and reactive ones. So the ratio for this is R equals 1 over 10 to the 12 e. This is something I would give you. You don't have to memorize that at all. But this is just a ratio, and it has to do with carbon dating. So like in this problem here, the ratio of carbon to carbon 12 is only this fossil is this. Estimate the age of the fossil. So this is our formula. So our formula is this. Again, something I would give you to not have to know how to memorize it, unless this is going to be like your future career or something. So that's the formula for carbon dating. So where T is time, if we're trying to figure out how old something is, we've got to figure out what T is. And R is the ratio of carbon. So in this problem, they tell us the ratio of carbon. The ratio of carbon is that. So that is our R. So we're going to go 1 over 10 to the 13th equals 1 over 10 to the 12th e to the negative T over 8, 2, 2, 3. And all we have to do is solve for the variable, right? So we're going to get this guy by itself. So step 1, get rid of that 1 over 10 to the 12th. Multiply both sides by 10 to the 12th. Over here, these cancel out, and we have e to the negative T, 8, 2, 2, 3. Over here, 10 to 12, 10 to 13th. All of them cancel except for 1 over 10. If you're a little scared of that, you can also put in your calculator. Next, we got to get rid of the e, so let's natural log both sides. So these cancel out. I get natural log of 1 over 10, which will be some negative number. It goes negative T over 8, 2, 2, 3. Next, let's get rid of the 8, 2, 2, 3. So multiply both sides by 8, 2, 2, 3. And let's put that in a calculator. I don't know what that is. Over here, 8, 2, 2, 3 times natural log of 1 over 10. That should be some negative number. Natural log of 1/10 is a negative. So I get negative 18934.16 estimated about -t. Anytime you estimate, you want to put squiggly lines, so we know, okay, they rounded. Then get rid of that -1. So t equals about 18,934 years old. That's how old that fossil is, about 18,000 years. So that's how they figure out how old fossils are. They look at the carbon dating of it and estimate the logistic models. Okay, so logistic growth models are these curves right here. So that's another format I would give. You don't have to memorize it, I know how to use it. What happens here is it's kind of like bounded above and below. This makes logistic growth models cool. So the bound above is by this A here. That's kind of our horizontal asymptote. It's like here on a college campus of 5,000 students, one student returns from vacation with a contagious flu virus. It's a little too close to home. The spread of virus is modeled by this. Now, if you notice on top, it's 5,000, right? That's the number of students. You can't have more people with the flu than the number of students. That's why that's like the max. So when you have one of these, it's nice because they actually have a maximum. Anyway, where y is the total number of students infected after 2 days. So this is the number of students infected. T is the number of days. The college will cancel classes if when 40% or more of the students are infected. So first question, how many students are infected after 5 days? So that's just substitute in 5. So we're going to figure out how many students are infected after 5 days. There's some substitute 5 in for a t. And we'll put that in. And that's how we get up roughly about 54 students. So 5 days, then we get about 54 students. Next, after how many days will college cancel classes? So remember, cancel classes at 40% of the students are infected. 40% or more. So the main thing there is figure out what that is. And then we could plug it in. So 40% of the students, well, how many students are there? 50,000. 5,000, they keep on going higher. And that gets us about 2,000. So when 2,000 students are sick, they'll start canceling classes. So what we're going to do is plug that in for the number of students sick. We're trying to figure it out. So I'm going to get 2,000 equals 5,000 over 1 plus 4,999 dot e, sorry, to negative 0.8t. Okay, so how do I solve this? It looks a little messy now, and it's going to get a little messy. I'm going to cross multiply. Now here's the key. So when you cross multiply that, I'm not really going to multiply this other side. I'm going to leave it like this. Blah, blah, blah. I don't have space right now. Right? I'm not going to actually multiply this in. What I'm going to do now is divide by that. So let's divide by 2,000. I get 5 over 2 equals 1 plus 4,999 e to the negative 0.8t. Right? Now it's just a simple math problem. We're going to subtract 1. We're going to divide by subtract 1. That would give us 1.5. Let's get into decimals now. 4,999 e to the negative 0.8t. So next, let's get rid of the 499. So that's going to get us, I'll tell you right now, that is, I don't know what that is. These cancel out. Well, let's leave it the way it is. And then we get there, and then we can get rid of the e by taking the natural log. That cancels out. So we're going to leave, I'm going to leave this side like this. So 1.5 over 4,999 equals negative 0.8t. And then we're just going to divide by negative 0.8. And we get t is equal to roughly 10.14. So about 11 days, about 10 days. So after about 10 days, classes will start to be canceled. So there's that one. I think we have one more left. Log model. So here's a log model for Richter scales when they do earthquakes. So that's R. R is the magnitude of the earthquake. So that's how you figure out the magnitude of R of an earthquake intensity. I is given by this. So magnitude based on intensity. I0 is equals 1 is the minimal intensity used for comparison. Intensity is measured on the wavelength of earthquake. So in 2009, Crete, Greece experienced an earthquake that measured 6.4 on the Richter scale. So that was their R. Also in 2009, the north coast of Indonesia experienced an earthquake that measured 7.6 on the Richter scale. Find the intensity of each earthquake compared to compare the two intensities. So all we're going to do is substitute these values in for R and solve. Now remember, I0 is going to be 1 is the minimum intensity we're going to use to gauge. So let's do grease first. So their R is 6.4, so 6.4 equals log base 10 of I, which I'm looking for, over 1. So just that right there. So let's rewrite it. 6.4 equals log base 10 of I. Now remember, the way you get rid of the log is take the base of both sides. So this is a 10. We're going to take 10 to both sides. And then we get 10 to the 6.4 equals I. So that's the intensity of the grease one. Of the Indonesia one, it's 7.6 equals log base 10 of I. So same idea. We're going to take the base of both sides. These cancel out, and we get 10 to the 7.6 equals I. But we kind of don't know what this means, right? So that's why they want us to compare the intensities. So the easiest way to compare the intensities is just divide them. Let's put the bigger one, 10.6, over 10 over 6.4. Now, since they have the same base, we can just subtract the powers. So it's 10 of 7.6 minus 6.4, which equals 10 to the 1.2. And what's 10 to the 1.2? About 16. So that means that, right, we divided these two values, we got 16. That means the Indonesian one's 16 times bigger than the Greece one. So that's like the way that log and earthquake things work, right? It's the magnitude gets higher because we're doing log values. So it's 16 times bigger. Anyway, that's the lesson.